So welcome to the first session of the AAA conference, and this is going to be a very interesting tutorial by Manuel Bodirski. He's going to talk about oligomorphic clones. Basically, he's going to tell how to convert countably infinite algebras into finite ones. So please, Manuel.
Yeah, thank you very much. Thank you for the organizers for giving me the opportunity to give this tutorial. I will give a talk about oligomorphic clones. It has two parts. And the part today, Miklos already mentioned, the general goal will be that we take results that we know and love from finite universal algebra, and we try what can we say about infinite domain algebras. How much, what fails, and under which conditions can we maybe do the finite algebra results again in some maybe modified form. And today I will go over these basic results in finite universal algebra, and we'll see how in general they fail badly for infinite domains. But then there's one very fruitful assumption that you can have. It's oligomorphicity. And we'll see many examples. So the good news is oligomorphicity is not rare. There are lots of oligomorphic algebras. It's a proper generalization of the finite setting, and we'll present some results that hold in this setting. And this is today's goal. And tomorrow we will see more advanced results, very recent ones by Libo Barto, Antoine Moutet, Jakub Opperscha, Michael Pinska. Very recent results. And on the other hand, tomorrow will also be accessible because I will focus on applications. And the most important application that's guiding a lot of this research, which is recently done, is the constraint satisfaction problem. So this will be the running motivating example. But then there are also other applications. The applications of oligomorphic clones are not restricted to the constraint satisfaction problem. It's really for instance, there are very natural questions in finite model theory with relevance in database theory that can be attacked now with universal algebra if you are willing to do this step to infinite domains. Also, there is some very interesting work and very interesting applications to the theory of relation algebras. But this is also the topic of tomorrow, of the next part. All right. So let me start with some very basic results in finite universal algebra. I guess that you know most of it, but maybe what you don't know is how these things fail over infinite domains. So we'll also have a look at that. So we have an algebra. So it's just a set with some finite arity operations defined on that set. And many properties of algebras are already captured by the clone of term operations of that algebra. So we look at terms that you can form over the signature of your algebra, and you look at the operations that are defined by those terms. The set of all those operations certainly contains the projections, certainly is closed under composition, so it will form what is known as a clone in universal algebra. And to study clones, we use relations. So we have to define what it means that a function or an operation of arity k, what it means that it preserves a relation of arity m on the same set. It means that if you take tuples in your relation, k of them, because k is the arity of your function, and you apply your operation component-wise to the tuples, you will again obtain a tuple, and you require that the resulting tuple is again in the relation. So it's a generalization of the concept of a homomorphism. So it's a k-array homomorphism. All right, this means that F preserves R. And now if you have a clone on a set A, you can go to the set of all relations that are preserved by all operations in the clone. This is denoted by inf of C, set of invariant relations. And you can go in the other direction. You can also start with a set of relations And you can look at the set of all operations that preserve these relations. This will be denoted by pol of R, the set of all polymorphisms of the set of relations, the set of all operations that preserve every relation in the set R. And now, what we can also do, of course, is we can start from a clone, go to the invariant relations, and then go back. Now you start, you do first inf, and then you do pol. Certainly, you will contain all the operations you started with. Pol of inf will contain all the operations you started with, but it potentially more. And the fundamental result that you know, and that's so fruitful for finite domains, is that if the set is finite, the base set is finite, if the base set is finite, you will end up with precisely the same set of operations you started with. All right, so this is something we would like to have on infinite domains as well. But what do we get, in fact? So let's have a look at an instructive example. So the base set here is the integers. Yeah, and I will look at two special operations. Sn is the shift operation. I shift by n. I map x to x plus n. It's a unary operation. And I also look at a transposition. Say the transposition that flips the elements 0 and 1 and keeps all other elements at their place. So it's the identity everywhere else. It's a transposition. And now we know, well, with transpositions, you can generate a full symmetric group. And so let's look at the algebra that contains the shift by 1, the shift by -1, and this transposition. Certainly, the set of all term operations will be countable because we have just 3 operations and there are countably many terms I can produce, so we have countably many operations. But if I look at the clone of term operations, then take a look at inf, and then look at pol, I claim that I can produce, that I will find in this set, I will find uncountably many. I will find all injections in this set of operations, all injections from Z to Z, and that's uncountable. So indeed, we got some new operations here. So the result will not hold literally, but I will illustrate and I will explain in the following this classical facts that show us that the picture is not as ugly as one could. So it's actually a very, the closure, pol inf of the clone has a nice description. It's still well behaved, even though the base set is infinite. We have to, though, look a little bit at some topological concepts. So what we have to do to understand the closure is we take the discrete topology on the base set, and we equip the set of all operations of arity k, a to the a to the k, by the product topology. Now we have an arbitrary exponent. A is discrete, so we equip a to the k by the product topology. The basic open sets in this topology will be given by fixing some finite number m and fixing some m tuples, a1 up to ak, and a0, also an m tuple. And then the basic open set of this topology will consist of the set of all operations of arity k that map a1 up to ak, component-wise again, to the tuple a0. And we can equip the whole space of operations on A. We can equip with the sum space. This will give us a topology. It's a very nice topology. The clone composition will be continuous with respect to this topology. And now the very nice fact here in this context is the closure with respect to this topology of the operations in our clone will precisely give the relations that are, will precisely give the operations that preserve all invariant relations. So it's not difficult to see, and it's quite nice, and it will be useful in the following. All right. Now, we looked at polinf. We can also look at infpol. So this time we start with the relations. Then we go to the operations, and we go back to the relations. So we look at a set of relations on a common domain. We may view it as a relational structure. It has a base set A and some relations, and we look at the polymorphisms of the structure, set of all operations that preserve all relations. And then we go back, we look at the invariant relations. For finite domains, this is again very fundamental, very useful in universal algebra. We understand precisely the relations that we get on top of the relations that we started with. It's relations that are primitively positively definable in the structure we started with. What's a primitive positive definition? So it's a restriction of first-order logic where you are only allowed to use existentially quantified variables, and you are allowed a big conjunction of atomic formulas. Formulas that are built over the relations you started with by just applying them to the variables. And relations that you can define in this very restricted form over the relations you started with, they will be, it's an easy exercise, preserved by all polymorphisms, and therefore they will be in the set. And the theorem, the nice theorem is that these primitive positive definable relations will be all relations in inf of pol. This has very important applications that will be used tomorrow in tomorrow's part, in part 2 of my survey, in constraint satisfaction, because these primitive positive definitions are precisely those that preserve the complexity of the constraint satisfaction problem. So this has important applications in theoretical computer science. All right, so let's look at this on infinite domains. Again, I will start with an example. Again, my example will have as a domain the integers, and I equip my structure with the following relations. I have a singleton relation unary that just contains 0. I have a binary relation that just contains the successor. And I have a 4-array relation which contains all 4 tuples, so that if A equals B, then C equals D. Now, this is the structure I want to start with. I look at the polymorphisms. What are the polymorphisms of this structure? So all unary maps, they have to preserve 0. And because of the successor relation, inductively you show they have to preserve every element. So we have only one unary operation in this clone, namely the identity. Now we also have this funny relation, and this funny relation has the effect that every operation that preserves it must be essentially injective. So if you look at all the arguments on which this operation depends, and look at the function that just is defined on those arguments, you have an injection. And now if you have to be injective and you have to preserve the successor operation, maybe I forgot one relation. Maybe I also want to add the relation disequality. You will find that the only operations that preserve all these relations are the projections. You killed all operations. So if you go from A to pol of A, and from pol of A back to the invariant relations, you will have all relations on A. So it seems that you, by going to the polymorphisms and going back to the relations, you lost all information. So that can be quite pessimistic, this picture. And yeah, but still, you could still try to characterize inf of pol in general. And there are some descriptions by many different authors. And maybe the audience, I have such an expert audience here, maybe if someone knows an account which would not use infinitary relations or projections where you project away infinitely many things. All of the approaches that I found explicitly in the literature mention they use infinitary relations to characterize inf of Poll. But what is well known, but I actually, as I said, I don't have a good reference. So maybe some people in the audience have a good reference for this. It's actually, but it's true. You can prove it. It's not. It's so you also can describe the closure on an arbitrary set. Say on an arbitrary infinite, countably infinite set. You can describe it in the following way. You start with the relations in your set. You allow primitive positive definitions, but you also allow infinite conjunctions, infinite intersections over the relations you started with, and you allow direct unions. So in particular, what you want is that if you have relations R1 contained in R2, contained in and so on, and all the Ri's are in your set, then you want that the union is also in your set. And in this way, you will get precisely inf of Poll of A. Yeah, so I think this is a known fact, but I'm not aware of, yeah, please teach me the right place in the literature. I've searched quite a bit. As I said, the references here, to my opinion, they use infinitary relations. And the difference between infinitary relations and infinitary projection and just finitary relations is important in what follows. Let me also mention that you have to be careful here. It's not true that you would get all of the relations in inf of Poll by taking a direct union of an infinite intersection of primitive positive relations. So it's not enough to apply it in this order. You have to really close it. In particular, you have to allow arbitrary interleaving of primitive positive definition and infinite intersection. If you wouldn't allow, we have a counterexample with Marcello Mamino. So you have to be careful in this theorem. Huh? What's the nice consequence now is that if we work with relations of finite arity, suppose by some coincidence, maybe you have only finitely many primitive positive definable relations in your structure you started with. In this case, you don't need infinite intersection. If you just have finitely many different relations, you don't need infinite intersection. You also don't need infinite direct unions. Yeah? If these chains, if they are finite, you just take the last relation and you have it already. So if you have only finitely many primitive positive definable relations in our structure we started with, we have equality as in the finite. As in the finite, right? All right, and this is the motivation to look at the following definition, at oligomorphic clones. We'll define it algebraically. So we have a clone. I will look at the unary part of the clone, the set of all operations of arity 1 in the clone. And I look at those operations that are unary, that have an inverse in the unary part of the clone. So I want U composed V equals V composed U equals the identity. So the set of all invertible unary operations. If you look at those, they form a permutation group. Easy exercise. So we have a permutation group sitting inside the unary part of our clone. If your clone was the polymorphism clone of some structure, then these invertible ones, they will be precisely the automorphisms of the structure you started with. And now comes this definition, the central definition of this tutorial. I will look at what it means. That's actually a notion from model theory and permutation group theory, infinite permutation group theory. It's oligomorphicity. A permutation group is called oligomorphic if for every M, if you look at the action of the automorphism group component-wise on the M tuples of the elements of the base set, you want that in this action there are only finitely many orbits. This is, there are only finitely many sets of the form U applied to a tuple where U is an operation, is a permutation in your group. Yeah, there are only finitely many orbits like that. Okay, so this condition certainly implies what we had on the previous slide, because if a relation is primitive positive definable, primitively positive, it will be preserved by all automorphisms. So every primitively positively definable relation will be a union of orbits, and if there are just finitely many orbits, I will have only finitely many primitive positive definable relations. So oligomorphicity implied what we needed on the previous slide. And in fact, you have an if and only if characterization. And permutation group G is oligomorphic. Well, an automorphism group of a structure is oligomorphic if there are only finitely many first order definable relations. Let me write this. This FO means first order. So now I also allow universal quantification and negation and disjunction. And now it becomes an if and only if. Yeah. And this requires proof, but it's not so difficult. One can show this. And another equivalent characterization of oligomorphicity is that you may also look at the action of the automorphism group on the M element subsets of the domain. Yeah, so you map M element subsets of the domain to other M element subsets of the domain by your group elements. And if you have just finitely many orbits with respect to this action, you're also oligomorphic. And this is clear because you can certainly bound this number in terms of this number and vice versa. If one is finite, the other one is finite. They're not the same numbers, of course, but they bound each other up to some factor. All right. So this is oligomorphicity. And now I call a clone oligomorphic if it contains an oligomorphic permutation group in the unary part of the clone. I call an algebra oligomorphic if the clone of term operations is oligomorphic. We'll look at some examples. The first example is that we start with the group, the full symmetric group on the natural numbers. That's certainly oligomorphic. It's the biggest group you can have. And now you can produce from this group clones. Yeah? You just have to make sure that the unary part of your clone contains the full symmetric group. And an example would be the natural numbers with this equality and this relation A equals B implies C equals D that we have seen already earlier. That's just one example. This would be the clone of all operations that are essentially injective. It looks very restrictive, but in fact, there are Michael Pinsker and Hubi Chen and we proved this in 2010. There are uncountably many clones, closed even. Yeah, this I forgot. Even closed, uncountably many closed clones of this type that contain the full symmetric group. So this gives you a nice family of examples for oligomorphic clones where you can try to prove things. A next example is you start with the permutation group that preserves the order of the rationals, the automorphism group of the rationals. This is also oligomorphic. We'll see many arguments why later, but you can count the number of orbits on M tuples. And actually here it's maybe easier to count the number of orbits on M element subsets, because on M element subsets there will always be only one orbit for every M. And again, a clone of this type would be the polymorphism clone of the following structure where you have a ternary relation U is larger V or U is larger W. That would be an example. Now let's look at a non-example to get some intuition. We can look at the polymorphisms of the integers with the order. Now we still have only one orbit for the action of the automorphisms on points, because clearly the order on the integers is transitive. You will find for every number a and every number b, you will find an automorphism that shifts a to b. So there's just one orbit. But already if you go to 2, you look at orbits of 2-element subsets, I claim there are infinitely many. Because if you have two numbers a and b, and there are a distance k, and another pair that's at distance k prime, and k prime are different, they will lie in different orbits. You can't shift a pair at distance 2 to a pair of distance 3, for example. So we have infinitely many orbits on 2-element subsets. So it's a non-example. So maybe actually also, please, this is a tutorial, yeah? So I want to be very clear, very self-contained and everything. So if something is unclear, please interrupt me. You have this feature to lift your hand, and then Michael will broker the questions to me. And Michael is now, are you saying something? No. I don't hear you. I don't hear you. Okay. All right, let's continue. So the next topic will be the link between oligomorphic permutation groups and countable categoricity. So this is something in model theory. We will not use this theorem, but it's important to get some new examples. So this is a classic result from model theory. A clone is oligomorphic if and only if the structure, polymorphism clone is oligomorphic if and only if the structure we looked at is omega categorical. That is, if we look at the set of our first-order sentences that holds in this structure, this theory will have only one countable model up to isomorphism. Examples are Q. Cantor already proved that there are only every countable dense unbounded linear order is isomorphic. So this proves Q is omega categorical. Therefore, the automorphism group of Q is oligomorphic. Another example is the countable atomless Boolean algebra. Also the Rado graph, which is the up to isomorphism unique countable model of the almost sure theory of random graphs in, say, the model GN1/2. Yeah. So these are plenty of examples, classical examples, and for all those, by the explanations that I have already given, we know that inf of pol of A equals precisely the primitively positively definable relations in the structure A. You can also prove it directly, or you can use the argument that I gave earlier. All right. So this is the last page with examples, and to illustrate that oligomorphicity is not rare. Oligomorphicity is very general, is a very large class. Oligomorphic clones, very large generalization of finite clones on a finite domain. And to illustrate this, I need the notion of homogeneity. A structure is called homogeneous if whenever you have two finitely generated substructures of your structure, in my picture, these are these two that are isomorphic. You have an isomorphism between them, then you can extend this isomorphism to an automorphism. This is the notion of homogeneity. And it's easy to see that if your structure is homogeneous and has a finite relational language, it will have an oligomorphic automorphism group. Why is that? We have to count the orbits of m-element subsets. The orbit of an m-element subset is fully determined by the structure which is induced by these m-elements, by homogeneity. And because our signature is finite and relational, there are only finitely many choices. You can put a structure there on these m-elements. So that proves oligomorphicity. We'll call these also finitely homogeneous structures. Yeah? Finitely because the signature is finite and relational. So some examples of homogeneous structures. These are the well-known examples, Q and N. There are also some less familiar examples. And actually there are many results about classifying homogeneous structures for a given signature. And these classification results are very interesting, very fruitful, I believe, because they often produce very new, very beautiful structures. For instance, Lachlan, when classifying homogeneous tournaments, he discovered this very beautiful homogeneous structure that I have drawn here on the right. It's called S2. It's a tournament, so it's a directed graph, so that between any 2 points, there's an arc in either of the two, in one of the two directions, but not in both. And it's basically a local order. It's locally a linear order, which is dense, but only locally. Okay, and homogeneous structures, they can be produced systematically by so-called Freisee amalgamation, which makes them very combinatorially amenable as a class. So if I have a class of finite structures, which is closed under isomorphism and closed under substructures, and which has the amalgamation property, which is something that you can check. I will not go into details here, but it's a very concrete, very nice property. Then there exists an up to isomorphism unique, homogeneous, countable, I should say, countable is missing, countable structure such that the class of all structures that are finite and that embed into this structure, let's call it L for limit, is precisely the class you started with. It's precisely this class C of finite structures. So you have a unique, up to isomorphism unique limit structure, and it's homogeneous, this limit structure, and so this gives you a very systematic way to produce homogeneous structures in a finite relational language, and therefore oligomorphic clones. So let's stop the examples part and let's go to the universal algebra part. What can we do with oligomorphic clones? What can we prove about them? And we all know one of the very powerful things in universal algebra is the concept of a congruence. Yeah? We can analyze algebras using congruences. These are equivalence relations on the domain of the algebra that are preserved by all term operations and by all operations, by all term operations, therefore. So what can we say if our algebra we started with is oligomorphic? One nice thing is that we can form the factor algebra by the congruence, the standard construction. And the nice thing is if you started with an oligomorphic algebra, the factor structure will again be oligomorphic. Very nice. Huh? So we stay in the category we work with. We also have some extra things. Yeah? So that's things that we don't have for instance, we have only finitely many congruences. Yeah? Because we have finitely many primitive positive definable relations, finitely many binary relations that are first order definable even. So in particular, finitely many primitive positively definable binary relations. So we have finitely many congruences. That's very useful, of course, if you don't want to do arguments by induction. We also have something very particular. We have a unique coarsest congruence with finite classes. So how will this look like? So if A is my structure here, a unique coarsest with finite classes, right? So this might be look like this. Yeah, you have maybe lots of congruence classes of size 2, but infinitely many. Yeah. So this is maybe fine. This is maybe finite. You also have a unique finest congruence with finitely many classes. So you might have a congruence with just 2 classes. Yeah? And then there is a unique finest one of this type. These are, of course, very useful to know these. If you want to understand an oligomorphic clone or an oligomorphic algebra, it's very useful to know these two special congruences that are sitting around there. But of course, we might also have congruences that have infinitely many infinite. Yeah? And that's of course then interesting what's going on. All right, so congruences seem to work fine. Yeah? So this is nice. Let's look at another thing we all love, Birkhoff's theorem. In universal algebra, there's Birkhoff's theorem. So what's happening with oligomorphic algebras and Birkhoff's theorem? So let A be an oligomorphic algebra. We want to look at the variety generated by that algebra. Unfortunately, this variety will contain algebras that will always contain algebras that are not oligomorphic. Actually, the reason is the product. Yeah, we can form, for varieties, we are allowed to form infinite products, and that will be a problem for oligomorphicity. But there's a little twist to fix that. What we actually want to do, if you work with oligomorphic algebras, is we want to work with the pseudo-variety generated by the algebra. So here we only allow finite products. And then one can show that every algebra that is in HSP fin of the algebra we started with will again be oligomorphic. So that means we want to understand pseudo-varieties generated by. We need a Birkhoff theorem for pseudo-varieties. Yeah, that would be more interesting in the oligomorphic setting. And indeed, there is such a thing. So suppose we have two oligomorphic algebras. I want to understand whether B is in the pseudo-variety generated by A. Then this has an equivalent characterization. So I claim this happens if and only if the natural homomorphism from the clone generated by A to the clone generated by B exists. So what is that? So A and B are required to have the same signature, of course. Yeah, so we have a mapping which sends an operation in A to an operation in B that has the same name. And this, if we want to extend this to a clone homomorphism, we know for every term where it has to be mapped. And this is only well-defined if, well, in order to, yeah, we need this to be well-defined. Yeah, and the claim is here, this is, if B is in HSP fin, this is well-defined. Moreover, the map that's induced here from clo of A to clo of B is continuous with respect to the topology that I've introduced already. So that's quite nice, and it goes both ways. So that one might call topological Birkhoff theorem. Yeah. And there are two important corollaries that are important for also the applications in constraint satisfaction. So we can now look back and try to understand what this means if the oligomorphic algebra or the oligomorphic clone we started with is the polymorphism clone of a structure, an omega categorical structure. And this has a description in terms of the structure. Yeah? If the two polymorphism clones that are oligomorphic are isomorphic as clones, so there's a map mapping the operations in one clone to the operations in the other clone that preserves composition, maps the projections to the corresponding projections, and additionally is a homeomorphism, is continuous in both ways, then we know that this is the case if and only if the structures we started with are primitively positively bi-interpretable, where the notion of an interpretation comes from model theory, and usually they work with first-order interpretations. We modify the interpretations for model theory and replace, whenever you see first order, you replace it by primitive positive. We have another application here. If we have a continuous homomorphism to the polymorphism clone of the K3, that's the clique with 3 vertices, then we have a primitive positive interpretation of this structure K3 in our original structure we started with. So, and this will be the topic tomorrow, why this is useful for studying the complexity of CSPs. Another important topic is the topic of idempotency. Now, So far, everything worked out quite nicely for oligomorphic clones, but here it becomes more tricky, more interesting. So an operation, well, it's called idempotent. We all know that. If it, whenever you identify all of its arguments, it has to return that argument. And a clone is idempotent if all of its operations are idempotent. You see this on the relational side. A clone is idempotent if and only if it preserves all unary relations that just contain one element for every element of your domain. Okay. Now, the bad news is oligomorphic clones are never idempotent. Because what does it mean to be? If your clone is idempotent, it means that the group of invertible elements that sits in the unary part is trivial. So it will always have, if your base set is infinite, infinitely many orbits. So never oligomorphic. Of course, you still might have some interesting idempotent operations. I'm not saying that no operation in the clone is idempotent, but not the entire clone will be idempotent. And in fact, yeah, there are some interesting clones where no interesting operations will be idempotent. Let's look at this. This is a very interesting example. It's the polymorphisms of the inequality relation or disequality. It's an easy exercise and a consequence of a compactness argument that you have a ternary polymorphism here that's almost like a majority, but not idempotent. Instead of idempotency, which would require equals x, no, we don't have equals x, we have equals f of x, x, x. Yeah, and we'll call this a quasi-majority. Quasi-majority. And this illustrates an effect that will be important, in particular tomorrow. We get rid of idempotency, but we work with equations, and that's very important, equations that have height 1. This is a height 1 equation. There's no nesting. And yeah, every term that we use has precisely, we just feed in projections. So that the terms just have one function symbol and arguments, variables. All right, so that's idempotence. And to explain you a little bit how to fix this issue. Idempotent is important. Many results for finite algebras, they work with an idempotency assumption. Idempotence is very useful to prove things. And we can replace certain things by another property. I will explain why, how this is related later. But I will call a structure a model complete core if the automorphisms of the structure are dense in the endomorphisms, in the unary polymorphisms. So if you look at the closure of the automorphisms, you get all unary operations in the polymorphism clone. Equivalently, you can say a structure is a model complete core if every first order formula is equivalent to a primitive positive formula in this structure, for those who like to work with relations instead. And we have seen many examples. Yeah, it's easy to verify if you have say an endomorphism of Q, a unary polymorphisms of Q, it must be injective, and it will lie in the closure of the automorphisms by homogeneity. Yeah, so we have lots of examples already, but there are also non-examples. For instance, if we start here with the rationals, but the weak order, you will have endomorphisms that map everything to one point only, so constant endomorphisms. And they will, of course, be not in the closure of the automorphisms because things in the closure of the automorphisms will be injective necessarily. Okay. What's a good thing about clones, about model complete cores, will be useful later. If you have a model complete core, there is an operation that satisfies such an height 1 identity as we had it on the earlier on the previous slide. And I expand my structure by constants, finitely many only. Then the new clone, the stabilizer clone, will also satisfy this identity. Will also have an operation F which satisfies this identity. So this is a useful property that this assumption of model complete cores gives me. And now I think in order to allow some questions, I should jump to the end, and I will pick up what I'm missing some things that I will do tomorrow. But what I wanted to leave you as an exercise is the following, and then I finish. So suppose I have the following structure, and here I have some exercises for you until tomorrow. Tomorrow is my second part. You can solve these solutions until tomorrow, these exercises until tomorrow at 6. So I want to look at the following structure. I want to look at the infinite clique, K omega. I want to look at the Johnson graph. It's the line graph of the infinite clique, okay? The line graph of the infinite clique. You find the definition here. And I have the following exercises. My question is the polymorphism clone of this graph, is it oligomorphic? Yes or no? Why? Is it a model complete core? If not, is it homomorphically equivalent to a model complete core? And unfortunately, the other things you can't work on because I haven't. So I have to do this tomorrow, because I didn't manage. The other things rely on concepts that come on the slides that follow. But these two exercises you can do. Is the line graph of the infinite clique oligomorphic? Omega categorical. Okay, so let me finish and I take questions.